So, hello everyone to the restart of our international online seminar of interval methods and control. We are restarting now after a short summer break, and it's my great pleasure to introduce Thomas Chevet today, and he'll talk about interval observers for fault detection and estimation. And let's also briefly introduce our speaker. Thomas received his engineering degree in automatic control in 2017 from Supélec. And afterwards, he did his PhD in 2020 at the Université Paris-Saclay. And at the moment, he's a postdoc researcher at ONERA, the French Aerospace Research Institute. And he's currently working on the design of interval observers, fault-tolerant techniques in control, prognostics, health management, and also model-based or model predictive control. And now, Thomas, the floor is yours, and we're looking forward to your presentation.
Okay, thank you, Andreas, for this introduction. So, as was said, I am Thomas Chevet. I'm a postdoctoral researcher at ONERA, the French Aerospace Lab. And I will present results on the use of interval observers and zonotopic observers for fault detection and unknown input estimation in the context of fault estimation. This work was done from the beginning of my postdoc with Tagdin and Tarek Raisi from Conservatoire National des Arts et Métiers, and where I started my postdoc, and also with Julien Marza, who works at ONERA. This work was supported by the Paris-Île-de-France region, and a part of this work was also done with Zhenhua Wang from Harbin Institute of Technology, and I will mention him when the part we did with him will arrive. In this talk, I will consider linear time invariant and linear parameter varying systems, both in the discrete time and continuous time case. So this simple kind of models, with obviously in the linear time invariant case, the parameter vector being a constant vector. And these systems will be assumed to be subject to unknown but bounded perturbation signals and W and measurement noise signals V. In this talk, when I will talk about fault, I will talk about an additive bias on the state or measurement equation, but it could also be a modification of the matrices A, B, or C, or any design of any assumption that suits the needs of the studied strategy, and an unknown input, because I said we will deal with unknown input estimation. An unknown input will be an additive bias on the state equation that can be used in some context to represent a fault signal. So I will start with the description of a sensor fault detection strategy, in which we will consider a continuous time linear parameter varying system of this kind, which is, as we can find in literature, a good approximation of a wide range of nonlinear system classes and has the advantage of supporting the use of linear methods. A sensor fault, as I said in the general introduction, will be, in this case, an additive bias on the measured signal Y. And the problem, if we use the pointwise observer, would be the high risk of a false positive due to the uncertainties and the perturbation and model uncertainties that we have in the considered case. So, as we published in a paper for the European Safety and Reliability Conference of this year, in this paper, we proposed a robust interval observer to detect these sensor faults on this kind of systems. So for a bit of precision, the model we considered is this one, where we have a linear parameter varying state equation and a linear time invariant measurement equation, which can be subject to a fault signal. We have, as classically done in interval observer design, an initial state vector that is assumed to be bounded by bounded vectors, and a perturbation signal that is also unknown but bounded by signals having a finite infinity norm. We also assume that the parameter vector is unknown and unmeasurable, and that we can split the matrices, the parameter varying matrices, into a fixed matrices and a parameter varying one, which is unknown but bounded by two matrices, so for the matrices A, B, and D. We also assume that we already have a controller designed on the system to avoid having to design one here, so that the known control inputs and the state vector remain bounded over time. I also need here to recall some classical results for interval observer design. First, the positive decomposition of a matrix, that we can decompose any real matrix into the difference of two positive matrices. The first one obtained by replacing all the negative term by zeros, and the other one obtained by replacing all the positive terms by zeros and taking the opposite, so that we have a positive matrix. And this bounding lemma that allows us to find bounds to the product of a constant matrix and an unknown but bounded vector, and also bounds for the product of an unknown but bounded matrix and an unknown but bounded vector. So since we are we have difficult assumptions on the model, we consider a relatively simple fault detection strategy based on a pointwise detection strategy, in which we have a first sensor that is potentially affected by a fault, and a second, which is fault-free, and used with a pointwise observer, Lumberjay, Kalman, anything you might imagine, that is used to obtain an estimate of the state. Then this estimate is compared to the output of the potentially faulty sensor to generate a residual signal. And then if the residual signal is zero, the sensor potentially affected by a fault is fault-free. And if the residual signal is not zero, the sensor is affected by a fault. But the problem that will appear here is the limitation that we will have with this pointwise approach in the presence of perturbations is that, and of system uncertainty, sorry, is that the residual signal might be different from zero, even in the case where we don't have I'm sorry, could you turn your microphone off, please? Thank you. So I go back a bit. The limitation of this pointwise approach would be in the case of perturbation and system uncertainty and model uncertainties. Even if the sensor is fault-free, we could have a fault detected. So in the literature, we find a strategy that will consist in taking an additive threshold under which we consider that there is no fault. But here we consider an interval strategy where we replace the pointwise observer by an interval observer, generating bounds for the residual signal, and then as classically done with these strategies, if zero is in the interval that we just defined, the sensor is fault-free. But if zero is not in the interval, the sensor is affected by a fault. The problem that could appear here is for a low magnitude fault signal, because they would be drawn inside in the uncertainties and perturbations, and thus we might not detect them. But well, it would be up to the designer to consider if it's a problem or not. But here our goal would be to reduce as much as possible the size of the residual interval to detect the fault with the lowest possible magnitude. Therefore, we propose the following differential algebraic system as a framer for our states. So we have a differential part here and the algebraic part here, where in the differential part, we have elements that are bounds for the uncertainties on the model and on the perturbation acting on the system. And in both the differential and algebraic part, we have the introduction of two matrices T and N, which follows the strategy introduced by Zhenhua Wang and his team a few years ago, which consists in defining T and N satisfying this equation, so that we know that they have this expression here where C is a free matrix, thus introducing an additional degree of freedom in the tuning of the interval observer. Then if we knew perfectly the state vector, the residual signal expression would be this one. We don't know it. We have potential bounds for it. So with the bounding lemma, we can find bounds for the residual signal. And then we proved in our paper, as classically done, that if these two matrices are Metzler matrices, then in the fault-free case, the framer that we proposed in the previous slide provides actual bounds for the state vector. And then using the theorem and the bounding lemma, if these matrices are Metzler, in the fault-free case, the residual is actually contained inside the residual bounds, as we expect for the fault detection strategy. Then, for the framer to be an interval observer, we need the estimation errors, the upper and lower estimation errors defined here, to be bounded. Ideally, they need to be stable or input to state stable, asymptotically stable or input to state stable. Here, we can, with our strategy, we can only obtain boundedness. And we will base our reasoning on input to state stability, which with a condition presented here, where V is a quadratic Lyapunov function of the estimation errors gathered in vector capital E. Alpha and gamma are positive parameters to be selected or tuned, and epsilon here contains a part of the uncertainties on the system. Then I spare you the details of the computation, but we can obtain an expression about the time derivative of the Lyapunov function with here the matrix S that hides the observer gains. But we have a problem. We have almost the expression that we want for boundedness, but we have a problem here in the name of the vector capital Phi, which is a nonlinear function of the states, which prohibits us from directly concluding for the boundedness of the estimation error. Therefore, we found with the literature a bound for this quadratic term as another quadratic term, a quadratic expression of the estimation error and a positive constant. Here, the matrix Q and the positive constant B are functions of the bounds on the uncertainties on the uncertainty of the matrix A and on the bounds of the estimation potential estimation error. Then we can obtain an upper bound for the Lyapunov function's time derivative like this. And then if we find matrices S and P so that this matrix capital lambda is negative definite, the estimation error, we can conclude that the estimation error will remain bounded over time. Then if we remove the negative term on the right-hand side of the previous on the previous bound and we integrate the resulting inequality, we get this bound for the Lyapunov function on the system. We gather the dynamics of the residual bounds in this matrix form. And then if we have this, we can prove that if this condition is satisfied, just bounding V with this expression here, that we will have this performance for the observer with the norm of the residual bounds of the residual interval bounded by a vanishing term here and a constant term here. And this inequality is satisfied if this linear matrix inequality is satisfied. Then we can obtain the observer gains by minimizing the parameter mu that is here. So minimizing the bound of the norm of on the residual interval. Under this linear matrix inequality constraints, this one imposing that the state matrices of the observer are Metzler as expected. This one imposing obtained from the boundedness condition, and this one obtained from the performance condition. Then we get the observer gains if we go back some slides for the definition by just taking this product here, y and p being decision variable of the optimization problem. Then we tested this strategy on a simulation case with a dampened mass spring system with some uncertainty on the dampening of the dampening parameter of the spring. So the state vector is the horizontal position of the mass and its horizontal speed. We consider the uncertainty on the dampening to be a sine wave, just for the example. We have our input signal and our perturbation that is bounded. We have here the definition of all the fixed and parameter varying part of the matrices of the system. And by choosing a value of the matrix C, we have T and N, as well as the bounds that we need for the optimization problem. And we can solve the optimization problem, obtaining this value here for mu and these values for the gains. This that we define here. So we see that in this part, and this part, we have the interval is centered on 0, which is expected. We have no false positive. We don't have the fault signal is 0, so the interval is centered. But between 2 and 4 seconds, we have what we want. The interval is shifted because we have a constant fault. But here we also have another fault, which is a ramp signal. And we see what I said at the beginning, that it appears at 7 seconds, but we can't detect it until 7.3 seconds, because before that, the fault signal is too low. So now that we have seen a strategy of fault detection, we will study unknown input, which are for fault estimation. So in this case, we will consider a discrete time linear time invariant system that is subject to an additive bias on the state equation and the same perturbations, bounded perturbations and measurement noise as before. And the problem with the use of Pointwise observer is that we have uncertainties is now uncertainty appearing on the Pointwise estimation of the unknown input. So we proposed in a paper published this year in collaboration with Zhenhua Wang a zonotopic Kalman filter interval observer estimating both state vectors. To be more precise, the system we consider with the additive bias here. We consider that the initial state vector is contained in center and this generator matrix. The perturbation and measurement noise are their absolute value is bounded by a positive vector, so that we can say that they are contained in a zonotop centered on 0 here, with generator matrices obtained by taking diagonal matrices with diagonal elements, the positive vectors that I just talked about. And then we need a strategy to estimate both the state and the unknown input. In the literature, we find several approaches. So ones which will define an evolution model for the inputs with the here of source of uncertainty. So well, which will be which is a problem, as I said at the beginning of this part. And we also have we use the part I forgot. We add this model. We augment the state with this new model, and with both the state and the unknown input with this new state vector. Or we can also find strategies splitting the system into 2 subsystems, one free of the influence of the unknown input and one influenced by this unknown inputs. The first one is used to estimate an image of the state vector, and the second one is used by using the inverse transformations to estimate the state vector and the unknown inputs. But since we have change of coordinates, we introduce again uncertainty on the estimation. So here we decided to consider another approach that we can find in some papers in the literature. It's to add the previous value of the unknown input to the state vector like this, so that our dynamics can be rewritten as descriptor dynamics. The matrix E being obtained just like this, and the other matrices being just the matrices of the state space version padded with zeros to get the right dimension The only other modification we need is the modification of the initials, the zonotop containing the initial new state vector by padding the center and the generator matrix with zeros. Then we do this assumption, this classical assumption that this matrix has full rank. And then we can find two matrices T and N so that this equation is satisfied. We find again the expression of the matrices T and N that we had for the previous for the fault detection strategy, except that I and C are replaced by E and H. And then by multiplying by Z at time k plus 1, we get these dynamics that will be used to design the zonotopic observer. The estimation strategy will then be a prediction correction strategy with the prediction going like this. If the state vector is contained, the descriptor vector is contained in this zonotop at time k, then at time k plus 1, it will be contained in the predicted zonotop with this center and this generator matrix, both being obtained with classical operation, with the results on classical operations on zonotops. And this here is just the order reduction operation introduced by Christophe Combastel, which consists only in sorting the generators of this generator matrix by decreasing norm, and then if if the zonotops has less generators than the maximum number we want, we don't touch the generator matrix. Otherwise, we keep the first ones and we bound the last ones, so the ones with the lowest norm, by a box defined like this. Then at time k plus 1, we know that from the measurements that the descriptor vector would be contained in a set here, which is the intersection of a finite number of strips, as much strips as we have components in the measurement vector. And the strips are obtained, each strip for each component of the measurement vector is obtained by by taking the inverse of the measurement equation. Then if this is necessary, I mean by that, if the strip is larger, the intersection of the strip and the predicted zonotop is larger, like here we have the green area of the strip, which does not intersect the predicted zonotop, we tighten the strip with the strategy from the paper of José Manuel Bravo from 06. Then for the correction step, we assume that our predicted zonotop are generators, and then we introduce this notation just for readability when not having the explanations. We will compute with the strategy introduced in this paper a family of R zonotops, so that the intersection of the predicted zonotop and the first measurement strip is contained in every zonotop in the family. And then we will select the first corrected zonotop as the one of the family, minimizing the Frobenius norm of its generator matrix. Then if we have more than one measurement, we repeat these steps by replacing here this zonotop by this one, and then recursively doing the same thing. And if necessary, we tighten the corresponding strip to have a less conservative estimate of the. Finally, when we don't have any more measurements, we call the corrected zonotop, the estimated zonotop, the last one that we obtained with this strategy. We tested this strategy on a simulation example where we have here a linear time invariant system, a stable linear time invariant system. We have here the initialization for the necessary zonotops. We have a sine wave as input signal, a sine wave as unknown input, which shows the matrix C to be 0, so that we have this matrix T and this matrix N, and the maximum size of the maximum number of generators considered for the reduction order in the prediction step is 20. And by of the estimated zonotop and adding the sum, adding and removing the sum of the absolute value of the generators, we have intervals containing each component of the state vector and the unknown input. And we see on this example that we have a better performance that a strategy using the splitting the system into two subsystems, but that is expected because, as I said, this strategy introduces additional uncertainty due to the change of coordinates. But we see, so here we have these bounds on green on the figure, our bounds are in red. And well, we don't see it because it's more or less superimposed, but our strategy is on, the performance of our strategy is on par with another strategy found in the literature where they use a pointwise observer in which H-infinity criterion is used to tune the matrices T, N, and L. And then they propagate a zonotop containing the estimation error around this then since we didn't matrices T and N, we assume that if we choose a suitable criterion, we could optimize their values in order to, of the matrices T and N, sorry, in order to improve the performance of the resulting observer. Then for the last part of this presentation, I will also talk about unknown input estimation, but this time I will consider an discriminating system. So I have the same assumption that I have an additive bias on the state equation, and I have the same. We would have the same problem as in the zonotopic case with a pointwise observer. Then, in a paper yet to appear in the next conference on decision and control, we proposed a robust interval observer used to estimate both the state and an input, as in the zonotopic case, but now for linear parameter varying systems. So, for more precision, the linear parameter varying system that we consider is this one with the additive bias here, a linear time invariant measurement equation, and unknown but bounded perturbation and measurement noise with these properties the same as in the continuous time case. And again, we consider that the parameter is unknown and unmeasurable, but that we can split the parameter varying matrices into a fixed and a parameter varying part, the parameter varying part being unknown but bounded. And again, we assume that controller has already been designed for this system, so that the known input and the state vector remain bounded over time. Then for the estimation strategy, we consider exactly the same thing than with the zonotopic observer, but here we have parameter varying matrices instead of time invariant matrices. That can be again split into a fixed part and a parameter varying part by just using the same decomposition for A, B, and DW. Then we make the same on the rank of this matrix. It has to be a full rank, to have full rank, so that we can find matrices T and N satisfying this equation, so that they have this expression with C, again a free matrix, and by multiplying by Z at time k plus 1, we have these dynamics that we will use to design a framer and an interval observer. The framer we proposed is this one, which is similar to the one we had in the continuous time case, but here we also have this term bounding the measurement noise that didn't exist in the continuous time case. And then we can prove that if these two matrices are positive matrices, classically, we have the signals generated by the framer are actual bounds for the descriptor vector Z. Then, by following the same steps, I don't recall them here for brevity, by using the similar steps as in the continuous time case adapted to the discrete time case, we say that we can obtain the observer gains by minimizing parameter under these constraints S, that this matrix S that hides the matrices T F0 minus LH is positive, This linear matrix inequality is obtained for a boundedness of the estimation error, and this one is here for to get this performance here with the norm of the estimation error being bounded by a vanishing term and a constant term. And then again, the observer gains are obtained by taking this product here of the decision variable of the optimization problem. And again, we tested this strategy on a simulation scenario with these matrices. So here we have the fixed part of our matrices, here the time varying part. We have the necessary bounds of the initial state vector and on the perturbation and noise. We have this controller here, this output feedback controller, and again a sine wave as a non-input. We chose Xi to be 0, so that we have these matrices T and N. And after tuning, we get these intervals for each components of the state vector and for the unknown input here. We did not compare these results with existing results because they are almost known using exactly the same assumptions as we had in our approach. And again, as in the zonotopic case, we think that we could improve the performance by tuning the matrices T and N with a suitably chosen criteria. Now, as a general conclusion on this presentation, I will remind that in this presentation, we introduced an interval observer-based strategy for sensor-fault detection on the one hand and for unknown input estimation on the other hand for linear parameter varying systems. And to tune them, we defined a linear matrix inequality-based optimization strategy that allows for the inclusion of additional constraints if necessary for the considered application. We also introduced a zonotopic Kalman filter unknown input observer for linear time-invariant systems. And in future work, we would like to find the optimal tuning of the weighting matrices T and N to adapt the fault detection strategy to detection of other types of faults. And finally, to adapt the zonotopic Kalman filter to linear parameter varying systems. So here are the references I introduced in the presentation that you have a presentation that will be available on the seminar website. And I thank you for your attention. I can answer any question that you might have.
Okay, thanks a lot, Thomas, for a very interesting presentation. And yes, as you just said, the talk is now open for discussion. Who wants to start with questions?
I see.
So is there anyone who has raised their hand?
Raised the hand.
If not, let me start.
Andreas, there was a question.
There's a question, okay.
Yeah.
Okay.
Carlos, please go ahead.
Sorry. I have a problem with my macro. So basically, thank you for very nice talk. It was really nice, and actually I like it, and I would like to discuss some simple things. Could you go for the slide 9 and 10? It's just
9 and
that, something that for me, and I'm not sure what is this about, and I would like to use your strategy actually because it sounds really great. But what is a fault-free sensor? I mean, because if I have a fault-free sensor, why don't you use this kind of sensor and that's all? I solved the problem. I don't need to detect any fault now. So how do you design this fault-free sensor? Because that for me is the main problem. I don't know how to validate with a sensor that it doesn't exist, or it does.
Well, actually, here the thing is it's something that I didn't explain. The thing here is you would have several sensors and compare each to the others. As you have, for example, or let's say on a plane with the altimeters.
Of sensor, and I take the average, something like that.
Sorry.
A grid of sensor, and I take the average.
Yeah, and you would compare everything, and you will compare all the sensors between them, and detect which one have faults, and trust the ones who don't have faults, and do not trust the ones who are faulty.
So in practical, so it's not a fault-free detection. So if I produce a hue detection, I mean, let's assume an attack, and I produce a hue fault in more sensors than one that is there. One sensor, this is the one you a right answer. This
this is a first approach, because we consider approach, as I said, because assumptions on us that where is it here? That well, we already have uncertainty provoked by the perturbations, but we also have uncertainty on the model that is unknown and unmeasurable. So we all so since we have already a system with how to say, which is already a bit horrible to deal with, let's say, we consider in a first approach a simple strategy where the problems that you are mentioning are the next step in the work, but are not yet considered.
And now, could you go to the slide 21? Sorry.
21.
Yes, and
here.
No, it's not this one. Could you go back?
Okay. On which part was it?
It was about the stability of the observer.
Yeah, it was like here. It started here, and then we had.
Yes. We can move forward.
Yeah, we have
sorry.
this.
It's when you find the bounds. You found the bounds in some points. Here it is, I think, and these are the bounds, right?
Yeah.
BT, the first equation actually define the bounds that you're gonna be decreasing. But when I see this, I'm assuming that you are starting in your graph from this bound, because I never see any reduction in the graph. I always see like the bounds we're keeping. Okay, and I know that you're gonna have some decreasing, of course, and you're gonna have some bounds. But basically, when I see, and this is what I see, I mean, maybe I'm wrong. I see the bound is just keep it continuously.
Yeah,
so
actually, this is the worst case. This is the worst case bound that in. This is the highest that we have, but might not be the real bound that we actually see here. This is just the worst case. This is like an H infinity. This is an L infinity criterion, but this is actually the bound that we have. That our the norm that we have here, the norm here cannot go higher than this value over time, but nothing prohibits it to be lower or way lower than this bound.
No, of course.
But we cannot.
To decrease to that point. I see your bounds are almost constant.
It decreases.
When you notice, okay, no. Sorry, I'm talking about. Okay, this is definitely the wrong. The wrong slide, because I think it was for the zonotopic section where you have some kind of sign. And
zonotopic, yeah.
When you see here, all the bounds look like you start on one bound and you just keep it.
Well, actually, here, if you look, because I initialized to a small value, it increases at the beginning. It's quite small. Maybe I don't know if I can zoom in without losing everything. But actually, it increases a bit at the beginning because I chose an initial value that is quite small. So at the beginning, you have a bit of an increase, and then it decreases. And on the unknown input, we don't see it because everything is shifted by one element, because I used the previous element. So we don't see this behavior at the beginning because of the shifting. And here you see the behavior of the evolution at the beginning, and then you remain more or less constant. well, it happens quite fast because of the tuning of the observer and the design of the. We reach quite fast, more or less the final value of the width.
And you use the zonotopic order observer for Compastel. He used the optimum based on the Frobenius norm, of course. It's not the best, but it's the optimum. So the next section that you have to tune this parameter it doesn't have a sense because this is the optimum already with respect to zonotopic intersections.
Yes, but we could also, the thing is, we could also try and see what happens if we tune the prediction in the prediction step, if we try to minimize first in the prediction step the predicted zonotop, and then use the optimum in the estimation step.
Okay, the problem is that in my case, it's not your problem. The problem is that you present many different approaches and different strategies, because one of the things that you present, it was the zonotopic intersection. I mean, the zonotopic Kalman observer. And this zonotopic Kalman observer do not have the prediction section. Actually, it's like a Lundberg observer, and you don't produce the intersection, but you also produce it. And could you go for the slide 44? I hope that this is the slide. Yes. Could you explain me this framer a little bit more, because
no, this is the topic. Came back to interval approach. In this part, this is not. It's maybe I went too fast when I introduced it, but we are dealing with an interval observer and not a topic Kalman filter.
Okay, got it. Okay. No, actually, that's basically my question. I want to check.
Okay.
I'm checking actually your paper right now.
Okay, thank you.
Okay, many thanks. Do we have any further questions? So I have to be honest that Carlos has stolen some of my questions that I already had. But he didn't ask one of the questions, and this was on the Outlook slide. At the end, you mentioned that you want to go on into the direction of actuator fault diagnosis.
Yeah.
And more or less, this is I think, a little bit of a philosophic question. When we're looking at your system model where you have those input matrices multiplied with the physical input U, and the disturbance input matrix multiplied by D. Would it be just the thing that you just set both matrices identical, and then you're trying to estimate the corresponding variations of the applied system input with respect to the actual one, or do you have something different in mind?
Yeah, no, actually, it's a sentence I was not really clear. I was talking on this part about the linear time invariant case, the linear parameter varying case in continuous time, in which we do not have yet studied. I did not present an unknown input estimation strategy in this case. So I was talking about this case. In
okay,
which
this was only related to the to one of the parts of your talk, and not to the complete one. Okay.
Yeah, it was just for the fault detection strategy at the beginning, and not for the subsequent strategies.
Yes, because for the other one, I would say you already have an actuator fault diagnosis.
You're totally right with this. It's
yes,
I already have the detection.
Yes, but when you have the detection of the actuator fault, do you also think of strategies how to compensate this fault?
This is also a next step.
Without losing stability.
Yeah, I was not exhaustive with the list of future work. I just gave some quick ones that we can take from what I said. But yes, by looking further, we could try to see what happens using this unknown input estimation to compensate the fault and to have a fault tolerant control, because here we have detection and a sort of isolation of the fault. So the next step is actually trying to mitigate the faults. But it's also potential perspective of this work.
Yes, and then I have a further question related to the slide 18. where you mentioned that the matrix P is a diagonal matrix. Yes, it was in your theorem. You say you have a matrix P of some given dimension, and you're setting it to a diagonal matrix.
Yes.
I think this could be, or it helps you to simplify the test for cooperativity. But it may be restrictive. Maybe you don't find a solution because of using a purely diagonal matrix. And if something like this arises, do you have any, let's say, workaround how to continue in such cases?
That's a good question, because here, actually, yes, I only consider the condition given in this paper, which is to check that this matrix is Metzler. It's just adding a diagonal matrix so that the entire matrix is positive. But yes,
it's because I think you would need to do something, a change of coordinate, in order to modify the matrix S.
Yeah, or you would have to do that, or check or have other constraints to bound the influence of matrix P, but you will have to know the sensitivity of the sign of every element of the resulting matrix depending on the elements of P, and I guess it would become a really complex problem. What I'm describing
because
right
if
now.
you have this, if you're modifying all the matrix entries in P, that's, what is it, 4 times n square elements that you have at the end as additional decision variables. And that's really tough.
Here at least we have a limited complexity, so maybe in some cases we could end up with a matrix P that cannot give us a feasible problem, but we could also play with the matrix, the other tuning parameter, which is the matrix C, the free matrix in T and defining in the expression of the matrices T and N, that could we could play with this degree of freedom to adapt it and to find a value of P that gives us a solution.
Okay, fine. And now, just out of curiosity, I would like to see the slide 16 again.
16.
Because that
yes.
There's this time derivative of the Lyapunov function candidate. There's the additive term, the additive positive term at the end. This reminds me of something. If you have some, let's say, linear system model with some stochastic uncertainty, and if you want to prove stability, you are generalizing the time derivative to the so-called Ito differential operator. And this gives also at the end such an additive positive term. And yes, I recently did some work also together with colleagues from the University of Wuppertal. And we used a strategy that if this additive positive term becomes large, there's some domain around the desired equilibrium of your system in which you cannot prove stability. And we designed for the stochastic case a strategy how to systematically try to reduce that area where you don't know what your system is doing. And this was a combined observer and also control strategy, an output feedback control, including an observer where we optimized both of them simultaneously. And I think that's just an interesting link here in the equation number 3. That looks very similar.
Because here, actually, this term is a problem to prove input to state stability, since it's a term that will not vanish if we shut down the inputs. But having an approach as you described could help to have actual stability and not just boundedness inside a given region.
Yes, and I think this has some links to the stochastic setting here as well. Yes, I'll send you the link afterwards to this paper.
I will take a look at it, because it could help improve the approach.
Okay, do we have any further question from the audience? Let's see, is there anyone unmuted? No.
I don't see any raised hands.
Oh, since there's no raised hand and obviously no further question, thanks again, Thomas, for your interesting presentation, also for us answering all the questions. And as for me, it's now, as usual, on Friday afternoons, always the duty to wish you a nice Friday afternoon, evening, and weekend. And we'll see each other again very soon in 2 weeks. And our next speaker will be Luc Jolin, and he'll talk in 2 weeks about one of his actual research topics. And now have a nice weekend and see you all soon.